In this video, I'm going to start discussing what's called the ontology problem in quantum mechanics. So ontology, which has to do with sort of what exists. So the ontology problem in quantum mechanics is what physical thing in the world is the wave function actually describing. So what is it out there in the actual world being referred to by psi, by the wave function? And so one of the things that's often sort of trotted out as one of the reasons that quantum mechanics is so strange is that it uses imaginary values which cannot be measured by any sort of apparatus, by any sort of equipment that we have. But quantum mechanics does not need to be complex. This is what Travis Norson, in the book I'm following called Foundations of Quantum Mechanics, is saying. He says that we don't need to use complex numbers. So we can have the wave function broken down into two different functions like this. So we have our psi here, and we have it equal to this f of x plus I times g of xt, where the f of xt and the g of xt are real functions that can be solved by two coupled real valued equations that look like this and this. And so these are like Maxwell's equations that are the coupled together of two fields, the electric and magnetic fields, which are very much real fields that can be measured in the real world. And so for electromagnetic fields propagating in empty space, these are the Maxwell equations, and these can actually be written like this. So as a combination of the electric field and the magnetic field with this imaginary number, where this F right here is a vector that's known as the Riemann-Silberstein vector. So this gives this right here. These could be rearranged into this form here, where we see that this part right here, we can then set that equal to this h hat, and then it looks very much like the Schrodinger equation. And so this is why Norson is saying that this the fact that we use imaginary numbers in quantum mechanics is sort of more of a formalism than saying something sort of, interesting about the actual world. So it's not giving us some, strange or deep insight into the actual world. It's more of a formalism in the mathematics. But where the ontology problem does really come into play for quantum mechanics is because quantum mechanics uses what are called abstract spaces. And so quantum mechanics uses a sort of multi-dimensional, even infinitely dimensional Hilbert space, but a Hilbert space is an abstract space. And so just kind of a brief overview of what abstract spaces are. So in the Newtonian and Maxwellian mechanics, we can always think about things in real 3D spaces, but there are useful abstract spaces, one of which is called phase space. And so we can think of a single particle moving in 3D physical space. It would have 6 dimensions in phase space. So there are 3 for position and 3 for momentum. But if we restrict ourselves to a single dimension, then we get a position on the horizontal axis and momentum on the vertical axis. And so if we think of a particle moving sort of in the plus x direction with constant momentum, which would have an equation that looks like this. So our position is equal to this momentum here times t divided by m, which just makes it into velocity plus our initial position. Then we get a horizontal line in the phase space that looks like this, where we see our x momentum is on this vertical axis and our x position is on this horizontal axis. And so our momentum is not changing, and so it's not changing in the up or down directions here, but it is moving in space, and so we see that it forms a line sort of moving that way. But we can also plot a harmonic oscillator in here. So a harmonic oscillator, such as a pendulum, will form an elliptical orbit. So we can think of the pendulum swinging back and forth. So as it moves in this direction, we see its displacement from 0 position, it increases, but it's going to slow down, and so its momentum decreases. And then as it moves this way, it moves back towards the 0, but its momentum is going to increase until it gets there. Then its momentum will decrease as it moves in that direction. So that's why we get something that looks like this, where when we are at the 0 position, our position is moving to the right and our momentum is slowing down as it sort of moves down towards 0. Then when we get to this position right here, we're going to start moving back to this direction, but our momentum is going to increase. It's going to increase in the sort of opposite direction, which is why it becomes negative. And so it forms this ellipse here in our phase space. And in fact, we can look at sort of various velocities and positions that look like this, where they form these sort of these ellipses here in phase space. And so inside these blue lines here, we have a pendulum that is sort of swinging back and forth. But if its momentum gets too great when we get into the red lines here, then so if we say we have a pendulum here, then what it's going to be doing essentially is moving completely around that way and coming back around. And so it's going to be forming this sort of full loop here in our phase space. But we can also think of what's called configuration space, which is it's very similar, but we just want to look essentially at the positions here. So for a single particle in one dimension, configuration space can just be sort of the real space that it occupies. So we have just the one-dimensional number line here, and we have a particle here in the positive x right here. And so this is sort of the real space, but it would also be the configuration space for that single particle in one dimension. But if we have two particles in one dimension, then the configuration space will have two axes. So one for particle 1, which we'll call that axis x sub 1, and one for particle 2, and we'll call that axis x sub 2. And so that will look like this. And so we see we have a particle 1 here, which is in the positive x direction, and a particle 2 here, which is in the negative x direction. And so on x1 for particle 1, it's going to be positive, but for the second particle in x2, it's going to be negative, with the sort of magnitude of those corresponding to how far it is from x equals 0. And just to kind of help make this more concrete, we can look at this. So if we have particle 1 in the sort of greater x, positive x direction, particle 2 in the less positive x direction, our x1 axis will be sort of this greater displacement from 0 there, and the x2 will be this less displacement from 0 there in the x2 axis. All right, and so if we want to look at just the particle 1 and particle 2 here, where particle 1 is the positive direction, particle 2 in the negative direction, then we can actually look at movement in this space. And so if we have particle 2 being less mass than particle 1, and we have particle 2 moving in this direction towards particle 1, where they will come together and sort of run into each other here, and it will send particle 1 moving that way, and particle 2 will bounce off and move that way. Then we actually get something that looks like this, where this red line here is particle 2 moving in this direction until it gets up to right there. Then it runs into each other, and now we have the green movement, which is represented. So the green movement is the particle 1 moving in the positive direction, and particle 2 bouncing off and moving in the negative direction. But in configuration space, that will look like this, where this thin diagonal line here is where these two particles will actually meet each other on this one-dimensional number line here. And so, yeah, you'll see these kind of abstract spaces used a lot in classical mechanics. So, like Hamiltonian mechanics in classical mechanics. But this is also the case in quantum mechanics. And so the wave function psi is also a function on three n-dimensional configuration space, where n is the number of particles in the system, where we can see, if we put this up into three dimensions. So if we, instead of having one dimension, blew this up into three dimensions, then we would end up with a six-dimensional space for this configuration space, because it's 3 times n dimensional. And so if we have two particles, it's 3 times 2, which is 6. And similarly, in quantum mechanics, we have 3 n-dimensional space here. So a single particle, this translates fairly well to 3D space, where we have this, but for n greater than 1, then it doesn't really translate that well into physical space. And so, in other words, if the wave function for a single particle, or more precisely, the product of the wave function as complex conjugate, is interpreted as a probability wave in real 3D space, then a wave function for n, this should actually be greater than or equal to 2 particles, is a probability wave in 3n dimensional configuration space. But then the problem is, how could we actually interpret that? And so this quote here from John Stuart Bell, he says that in this theory, the wave is supposed to be just as real and objective as, say, the fields of classical Maxwell theory, although its action on the particles is rather original. So no one can understand this theory, so he's talking about quantum theory here, until he is willing to think of psi as a real objective field rather than just a probability amplitude, even though it propagates not in 3 space, but in 3n space. And so Schrodinger himself said this. So this is in his wave mechanics, which is the thing that he submitted to the 1927 Solvay conference. And so he says in this, so what does the psi function mean now? That is, how does the system described by it really look like in 3 dimensions? Many physicists today are of the opinion that it does not describe the occurrences in an individual system, but only the processes in an ensemble of very many like-constituted systems that do not sensibly influence one another and are all under the very same conditions. And so this run-on sentence here. So if you remember in the previous video, I gave that quote by Einstein where he says that quantum mechanics must be describing an ensemble of particles. And so these are the many physicists that he is sort of describing here, as saying that this must describe not a single occurrence, but the ensemble of a great many particles. And so he says, I shall skip this point of view since others are presenting it. Presenting it at the Solvay conference is what he means. So I myself have so far found useful the following perhaps somewhat naive but quite concrete idea. So the classical system of material points does not really exist. Instead, there exists something that continuously fills the entire space and of which one would obtain a snapshot if one dragged the classical system with the camera shutter open through all its configurations. The representative point in Q space, where Q space here, he's talking about configuration space. So if you've ever taken like a classical mechanics, they use Q for sort of positions in this abstract configuration space. And so he's referring to this abstract configuration space. So the representative point in Q space spending in each volume element d tau a time that is proportional to the instantaneous value of the psi times its complex conjugate. So the value of psi times its complex conjugate, or if you want to simplify, you could just say psi squared, so the Born rule, for only one value of the argument t is thus in question. Otherwise stated, the real system is a superposition of the classical one in all its possible states using psi times its complex conjugate as weight function. And so what he means here by sort of like the camera shutter open. So with the camera shutter open, so if you've ever seen pictures that look like this, where somebody takes a picture of cars moving over a road like this, where their headlights and taillights sort of get smeared out like this because the camera has a shutter speed, and so the cars are moving, and so the time it takes for the shutter of the camera to sort of take the picture, the car has moved over some distance, so it smears things out. So that's sort of what Schrodinger is talking about here. So we have our particle, and so we have some region of space here. That particle is sort of moving all over that region of space, but it has a sort of classical, the particle exists as a classical object, but it's just moving over this space. And so this kind of goes back to what Schrodinger talked about before, how we aren't looking at something that is a cloud. We're just getting a sort of cloudy image of something that's very classical indeed. And so the time it spends, sort of in this small region right here is what he means by that d tau here. So some volume element of the space. And so the time it spends there is proportional to this Born rule. So the probability of finding it there. And so that's what Schrodinger is trying to say we can use to interpret what the wave function is. And so his sort of proposed solution to the ontology problem is that the wave function is sort of describing a particle that's sort of moving, that's sort of zipping around this space. And so the probability that is being described here is just sort of how much time it is spending in that amount of that sort of small region of space. But this issue, the issue too, is that psi is a wave in configuration space. And so we're not just saying that psi is a wave in real space, which is sort of the way you can interpret it in with a single particle, as saying that it's this probability wave in real space, whatever we might want to mean by a probability wave. But when we have multi-particle systems like entangled systems, then psi is a wave in configuration space. So we saw earlier that a particle in configuration space takes up a single location in that configuration space, but a wave will be spread out within the configuration space. And so Travis Norson, the author of the book that I'm following for this, says this in the book. So, but whereas a single point in 3 n-dimensional configuration space can be easily understood as an abstract representation of the configuration of n particles in 3-dimensional space, it is hard to see what kind of a field in configuration space might be an abstract representation of. That is, when we are dealing with a multi-particle wave function in quantum mechanics, it is simply not clear the way it is clear when we use configuration space in the context of classical mechanics of particles, what we are talking about. So Schrodinger's quote from above hints that we should not take the wave function seriously in an ontological sense, but in an epistemological sense. And so by that I mean, if we have this particle that's sort of zipping around, then the probability that we assign to it isn't some ontological claim, it's the claim of what we can know about the particle. Because if it's sort of zipping around, then we're saying we can only know that it's in this space at this for this amount of time, and so we assign a probability that it will be in that space when we measure it. But this view is difficult to reconcile with experiments like the double slit experiment, which suggests that the wave function does indeed need to be taken seriously as something that exists in some important ontological way, because the double slit experiment, as we saw in previous videos, suggests that a single particle is interacting with itself. So it's it's causing a diffraction pattern. It's destructively and constructively interfering with itself, which tells us that this wave picture of the particle is something sort of ontologically real about it. That because if we took Schrodinger's way of thinking about it, so we have our double slit here, then the particle, its wave is it's sort of zipping around, but it will still just take a single path through the double slit there. And so this suggests that it is a wave in some important ontological sense. But the take-home message here is that although the wave function psi is all there is in quantum mechanics, it's difficult to say just what sort of physical thing it is actually describing, especially for multi-particle systems. And so that's the ontology problem. What thing out there in the real world, what kind of entity is the wave function psi actually referring to? What sort of actual physical thing is it describing? And so that is the ontological or the ontology problem in quantum mechanics. And I will discuss this a little bit more in the next video. Then in the video after that, I will actually sort of go in a little more detail about what Schrodinger thought the possible solution to this ontology problem is. And so he expands on this idea a little bit more, but we will see that his approach kind of doesn't actually work very well for fixing the ontology problem. But Norson says that something like what Schrodinger is suggesting is probably a way to approach the ontology problem. But anyway, I don't want to ramble on too long. I hope you found this video interesting, and I will see you in the next one.